Perfect pitch, using the fast Fourier transform to create musical arrangements. My name is Anna Sue, and I'm part of the TJ Microelectronics Lab. How might amateur musicians identify pitches to create pop arrangements? Through an understanding of some cool math, we can create an implementation simulated in MATLAB. Have you ever listened to an instrumental cover, performed one either alone or with friends, or written a pop arrangement? If you haven't done any of the above, you should check out my YouTube channel for an experience. So like I said before, my name is Anna Sue, and before I'm an engineer, I'm also a musician. A lot of the motivation for this project originated from my background as a musician, as I began playing piano 13 and a half years ago and flute 8 years ago, so classical music has always been a part of my life. More recently, I also began composing and arranging pop songs, more specifically Mandopop or Taiwanese pop music. You can find out more about me musically at my music website, but the gist is I just really love music. It is incredibly easy to access music in today's world, whether through streaming on the internet, live performances, or other means. In particular, on streaming platforms such as YouTube and Spotify, it is also increasingly common to find instrumental arrangements of popular songs, which are often referred to as instrumental covers. Some famous performers of instrumental covers include the Piano Guys, Anna Menz, and Chewy Melodies. These can be written by a professional arranger or orchestrator to be used in a commercial capacity or for sale, but also by amateur musicians simply for fun. However, for the latter, without the original musical score, preparing such performances can require a substantial amount of work. Amateur musicians are typically incapable of transcribing and arranging full musical works within a reasonable amount of time, if even at all. It typically takes at least some degree of relative pitch, if not perfect pitch, to identify pitches in both harmony and melody. Even in that case, with the sheer number of musical lines occurring in the music, it may be easy to transcribe incorrectly. In the frequency domain, however, pitches are relatively easy to identify. In previous research, prior applications developed as early as the late 1970s included pitch correction and speaker verification systems. The former is now found in applications such as Auto-Tune, whereas the latter is often used in customer support calls. In this project, using the fast Fourier transform, also known as the FFT, we will extend on pitch detection algorithms beyond correction in order to identify pitches for musical score transcription, which can be beneficial in music analysis. In other words, the goal is to effectively create a machine that can spit out pitches it quote-unquote hears at any given period of time, like a person with perfect pitch. This can be accomplished with a MATLAB implementation of the FFT. Due to the convenience that MATLAB can provide with us for WAV files, we will import such files and identify frequencies within certain time intervals. Lastly, we will export the obtained frequencies as pitches on the A to G scale. With all this having been said, I hate math. The entire basis of this project is built on math. As previously mentioned, this project was implemented on MATLAB. We'll go through some of the background for the code that was written. The fast Fourier transform is an algorithm used to shift signals between the time and frequency domains. One of its most practical purposes is decomposing signals. Oftentimes, more complex signals are the sum of multiple signals at different frequencies. Through the transformation from the time domain to the frequency domain, those different frequencies and their respective weightings are able to be identified. As a result, the FFT is often used in applications such as signal processing. There are some important things that we should consider first before we begin. We want to minimize the duration of every clip so that it's reasonable to consider it a singular point in time to take an FFT. The first way we can do this is by identifying the key of the piece and if there are any key changes. By running the code on an entire audio sample, we were able to identify both things. The benefit of analyzing data in a format such as a vector or matrix is that some users may be able to pinpoint the timestamp of the key change and thus are able to separate a single audio sample into two to analyze, almost like two separate songs. Beyond splitting samples into sections of different keys, we can also split the samples into sections of beats, or strung pulses. This avoids the problem of time signatures, which are a way to organize beats into numerical groupings called measures. Within each beat, there are usually different rhythms, which are usually divided into groups that are in multiples of 2. However, it is important to remember that this method could present issues for music with swung beats, such as Mariah Carey's All I Want for Christmas Is You, or tuplets, because neither scenario fits into division by 2. For simplicity, we ignore that scenario. Taking the tempo, or speed, of the music into account through beats per minute, also known as BPM, we can calculate the number of FFTs we have to run through the sampling interval. It is not practical or necessary to take the FFT continuously, since a pianist is unable to actually play continuously. FFTs taken at discrete time intervals can reduce the calculation load to retain only the useful parts of an audio sample. As a result, in this project, there are two required preconditions: a WAV file and the BPM value of the audio sample. WAV files were chosen because of their lossless format and ease of interaction with MATLAB, and the BPM value can be found either as an exact value on Google or an approximated value through a tempo tapper, which can also be found through Google. With these two preconditions satisfied, we are able to proceed. This is important because we have to split the audio into rhythmic subdivisions in order to take the FFT. Through the audio read function of MATLAB, we can turn a WAV file into a data vector, which is among the reasons why WAV files were the audio format of choice. This becomes important as we try to manipulate the data that the WAV file consists of. We aim to find the number of intervals necessary within a certain audio sample. This involves three variables: duration, BPM, and the note value. Through the duration property of the audio info function of MATLAB, we can obtain the duration of the sample in seconds. By dividing the duration by 60 and multiplying by BPM, we can obtain the number of beats in the whole sample. Lastly, to sample every 8th note, we would divide by 2. To sample every 16th note, we would divide by 4, and the list goes on for every division by 2. Our end goal is to form a matrix where we can take the FFT of each column. Each column has effectively become a short data vector that represents a certain range of audio over time, which we can manipulate easily due to the nature of matrices in linear algebra. Conveniently, MATLAB offers a reshape function that permits us to easily do this. However, because the dimensions do not necessarily work out, we can also pad the matrix with zeros to indicate nothingness within a certain period of time. These steps result in the very useful matrix we shall call M. The FFT of each column is taken, made very easy by the colon operator in MATLAB. We can use a for loop to iterate through the columns of M. This is a very repetitive process that produces a lot of data. The final step would be to find the peak of every FFT and its associated frequency value. All frequencies are associated with a pitch from the A to G scale, spanning from A0 to C7, where the number indicates the octave. We could determine frequency ranges for the octaves, then frequency ranges for notes, and find the exact octave and note for that peak. Due to time constraints, this part of the project was not implemented. What does this result in? This is a screenshot of the 1,000th interval of Africa by Toto, where you can visibly see 3 large peaks. The larger the peak in a sample that we take the FFT on, the more the pitch is quote-unquote represented within a sample. In this specific sample, there are 3 main peaks at 122.636 Hz, 416.963 Hz, and 1,250.89 Hz, as highlighted above. These approximately correspond to B2 12 cents flat, G sharp 4 7 cents sharp, and D sharp 6 9 cents sharp, all of which are generally considered in tune notes. These notes make sense, since the key of Africa is A major. These 3 notes fall under either the key signature of A major or that of its dominant fifth, E major. It's hard to really analyze results manually on an individual level since so many FFTs are taken. In this song, the reshape matrix has dimensions of 1,798 by 3,655, meaning there were 3,655 FFTs analyzed on samples that were vectors of length 1,798. That's a lot of data. While this project does not necessarily seem very practical, it is quite impressive from a mathematical and computational standpoint. This project can be extended into a variety of directions, whether it is expanding upon transcription by including rhythmic or instrumental identification. Of course, it would also be very important to consider cases such as swung rhythms and tuplets, which we previously ignored, to ensure that regardless of which piece is inserted, we can produce an accurate arrangement. Researchers can also consider a more computer science-based method, particularly through machine learning, to improve possible inaccuracies originating from impurities such as noise and human error. Additionally, future researchers can also attempt to automate the process of creating transcriptions in software such as MuseScore. I would like to thank Mr. Gordon and Mrs. Ahn for their time and feedback and mentorship throughout this project, as well as Mr. Della Cuesta for asking me all of the crazy questions. Mr. Kosek also provided me with lots and lots of assistance with MATLAB code review and debugging, including further directions on where to proceed with my FFT research. Dev Patel also shared his endless, both solicited and unsolicited, assistance and opinions. Josh Lien lended me his moral support in forming an audio project. Sasha Suh, of course, came up with the original inspiration. I'd also like to give a shout out to all of my classmates in 4th period for their year-long companionship. Lastly, I would like to thank Mr. Bell for his unwavering support from the time I entered analog until even after his retirement, for answering every question, marking every schematic, and helping me with every crazy idea I ever came up with. His kindness and inspiration has certainly shaped the electronics student I am today, and I hope I will continue to make him proud in my future engineering endeavors. Here are our references. Thank you for listening to my presentation, and I hope you learned something. If anyone has any questions, please don't hesitate to reach out. You can find me either via email at hello@annasue.dev or through more contact methods on my website at annasue.dev.